There we go. Okay. So this is getting thick now, by now, this stack over here of class notes. I think I scanned today for the last couple of days, so you should get them. See if I can finish that block today. All right. So last page was 53, it should be 54. So page 54. Today we are June 1st. Okay, so we're going to be doing what you could see on the spring, on the monitor, which is equivalent springs. So this is a little bit similar to what you were doing in circuits 1 in finding what is the equivalent resistance for two resistance in series or in parallel. So what is the equation that we have at our disposition for the springs is F equal Kx. In electrical engineering will be what? Voltage equal resistance times intensity. Okay? So let's first do, if you want, let's switch the order here. Springs. So 1 in series. So what does that mean? You have here K1, we have here K2, and let's assume we have a force over here F. So this should be what? X1, X2. Okay, so if you have two springs in series, what would be equal on the two springs?
Force running through them?
The force running through them, okay? So the force is the same, and this would be X, but what would be X equal to?
The sum of x1 and x2?
Okay, X1 plus X2. So basically we have to do an equivalent. The equivalent should deform the same thing, no? So this would mean that it's equal to X1 plus X2. And from the equation F equal Kx, what is X?
F over k?
F over K. All right, but we see already that the force is the same for both of them, no? So we could say that will give what? F over K equivalent will be equal to what? F over K1 plus F over K2. See, we just mentioned that the force is going to be the same. Forces cancels out, and what we have at the end is that 1 over K equivalent equal 1 over K1 plus 1 over K2. Okay, and I'm just going to put here the general equation, but so if you have more than 2 springs, what should be the equation? It's 1 over K sub n, no? And you do here to whatever, to your number. All right, so now let's do the other case. So 2 will be springs in parallel. So we do the kind of the same process. So on the left hand side, I do the actual problem K1, K2, and what do we need to find? A K equivalent. And again, I'm going to do the force over here. Force over here. And X. So now, how can we find the equivalent spring?
Well, you know that the displacements have to be the same,
Okay, that's correct.
and then the forces would sum, and so you basically just work out the same process as before.
Okay, so basically maybe, so you could say what? The F over here. So F over here should be equal to what? F spring 1 plus F spring 2. So let me put this one. This would be F spring 2. This would be F spring 1, no?
Mm-hmm.
Okay? So same as before, so what will be F? Okay, so what was the equation we had for the springs? F equal Kx.
Mm-hmm.
So this will be equal to what? K1 x1 plus K2 x2 should be equal to what?
K equivalent X.
Yeah, equal to K equivalent X. Or what did we say about K1 and K2? Sorry, what did we say about X1 and X2?
They're equal to each other and equal to the total displacement.
Correct, so we have, if you want, here we have X1 equal to X2 equal to X. So it will give us K1 plus K2 x equal to K equivalent x, or K equivalent equal K1 plus K2. Or if I extend this to any number, will be what? Summation to the k sub n. Okay, I don't think you needed this for the exam at all. Generally, I don't like to give problems where you need to do that before solving the problem, but who knows, maybe you might have to do it. All right, so now we go to what I want to cover today. Page 56. So response. To base excitation. So let me do a figure and then we can try to understand the problem. So for the system below, so we have our mass M over here, we have our spring, we have our damper. Okay, so over here we're going to study the motion of the mass on top, so this would be our solution x of t. But what is special about this problem is that the base over here, so what's the title of this one? Response to base
Excitation.
excitation. So that means that the base is going to have the coordinates y of t, and that equation y of t here, if I could do this one. So the time response of y of t, okay, don't have to be this way, but it could take any shape. Let's say it would be periodic. So it's being excited. So this is y of t. So basically the base should be like a shaker. So it could be a shaker, but what could it be as well? Remember we kind of mentioned the problem of a car on the road? Mm-hmm. A road could also be the base excitation because it's not perfectly flat and it's not perfectly fixed, no? Okay? All right, so following what we did on the previous chapter, we need to derive the equation of motion for this problem over here. So we need to find the equations of motion. So we'll find equation of motion. So let's do a first thing three-body diagram, or some type of diagram. Okay, so this is the difficult part over here, so. How much will deflect the spring? Or the damper?
Would be Y.
Okay, but this is moving Y, then this could be going up or down, no?
Alright, so Y minus X.
So the deformation should be Y minus X or X minus Y, it doesn't matter, no?
Mm-hmm.
So this should be K X minus Y, and this should be C X minus Y. So the spring will be moving X minus Y, the damper X minus Y, the excitation is moving Y. How much is the block moving?
X.
X, so this should be what over here then? Mx double dot, no?
Mm-hmm.
Okay. There are different derivations of this in different books, but I think this one is probably not the shorter, but the one you at least see the physical meaning of every single term. So what is the second step on the procedure? To write down Newton's equations. So what will be Newton's equation for this system over here? What is the Newton's equation we're going to apply? Summation of forces equals to MA, because what type of motion is the block having?
Translation.
Translation. So we just do that on the y direction, but here we call it on that direction. So what will be the equation? Minus K X minus Y minus C X minus Y will be equal to mx of a dot. So this will give you what? Mx of a dot plus C at dot plus Kx, which is a classic equation. But now what's happening to this term over here? We're going to have terms in y, no?
Mm-hmm.
So we're going to have here Ky, and then what else?
See Y dot.
Yeah, this should be dots over here. Mistake, dot, 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 forgot to put the dots. Plus Cy dot. So, this is the equation of motion. What did we learn? What did we learn in the last chapter? Is to find the response of a system when it's subjected to a forcing function.
Mm-hmm.
So in this case, what's going to be our forcing function?
KY plus CY dot.
Ky plus Cy dot. So following exactly the same procedure, we should be able to find the answer, no? Okay? So same procedure, maybe it's like different algebra or final results. So Ky plus Cy become our forcing function. All right, there we go. So let's rewrite that solution. So let us find the solution for the equation what? Mx double dot plus Cx dot plus Kx equal to Ky plus Cy dot. Okay, so this over here now becomes our forcing function. All right, what is the procedure when solving the differential equation? When solving that equation, what do we do in all the other problems?
Assume a harmonic solution.
All right, perfect. So assuming okay, so we assume harmonic solution for what? For x to be capital X, E, I. I use capital omega, what would be omega? Would be the frequency of which function?
Of the forcing function.
Of this forcing function. This should have omega frequency. Okay? This will have some omega n. Alright, that will have to come. And we can do the same thing for y of t would be equal to the capital Y, E, I, omega t. Once we assume the solution, what do we need to do? We're going to have to differentiate this one twice the x and once the y, no? And then substitute into the equation. So let's see, we have x equal to capital X, T, I, omega t. X dot will be equal to what?
I omega x e to the I omega t.
Yeah. Will be equal to I omega capital X, T, I, omega t. And x of a dot will be equal to minus
Omega squared.
omega squared x e I omega t. And if we do for y, will be equal to capital Y e I omega t. Y dot is equal to I omega y e I omega t. So I will substitute into the equation of motion, which is this equation over here. What are we going to get? M of minus omega squared x e I omega t plus c I capital omega x e I omega t plus k of x I capital omega t should be equal to what? K of y, which is capital Y e I omega t plus c of I omega capital Y e I omega t. Okay, so if we simplify this a little bit, we can factor here by x e I omega t, and we end up with what? Minus m omega squared plus c I omega plus K equal to the capital Y pi omega t factor of K plus Ci omega. Okay, so what is the whole idea of assuming both responses in function of the same frequency, so that when we get to this step over here, we can cancel out the responses over here. What do we find over here? That x over y will be equal to what? K plus maybe
Ci omega.
yeah, better to write it under this form, I C omega divided by minus m omega squared plus I C omega plus K. Okay. All right, so we could leave the response in this form, but remember when we did the first frequency, we put everything in function of the ratio of the natural frequency and the forced frequency, no?
Mm-hmm.
But let's stop over here because for the understanding is the same thing. So let's go back to this problem over here. Look at the solution, all right? This is the solution, this is the assumed solutions. So generally what will be known? Will one of these two really be known or not?
Might be.
Which one can be known? In most cases.
Why?
Y of t could be known, no? So let's see, if it's a shaker, you can set it up to a certain frequency and to move to a certain amplitude. All right? So you know the omega, and you can know actually what will be the y. Okay? So then once you know that, what could you do with this equation? You could just say x equal to all this expression times y, correct?
Mm-hmm.
And then you will replace that x into what equation? That x will be this one over here. Okay?
Mm-hmm.
So if you want, you could do it over here, but we're just going to rewrite this under the more complicated form, but you could stop over here. All right, so go ahead. I don't want to misplace so 6. 58. Oh, next page is your exam here. 58. Okay, so recalling the expression for x over y, which is what? Go here. Okay. plus I C omega divided by minus M omega squared plus I C omega plus K. I don't know if to start doing the long way. Just do it a bit faster here. Well, let's do it a bit faster. I think you can always go. So the magnitude xy is equal to what? Remember how to do this?
Would it be if you square the two terms in the numerator, add them in square root?
Correct. That's what it is. But then you also have the bottom, so let's see if I have those class notes here. Let's see, force frequency right here. Oh, this is the exam. Okay, so okay, so basically, guys, let's see if we can see over here. What I'm trying to skip is a bit of like a bunch of work. This is the response for the force frequency. All right? So we have these responses, we went through the same process, and we get to this response. Then I saw you could write it under this form. Remember this one? And then we went through all this stuff of the algebra. So basically, what did we do? We did this conjugate, this is a squared plus b squared, but if you take the square root of that, what is that? This would be the magnitude, no? So instead of going through all these steps over here, all right, all these steps over here, okay, on the class notes, here the expression, then we add all these expressions over here. We're going to do the same thing, but I'm going to take a little bit of a shortcut over here. Okay, we ended up to this expression. Remember, we had at the end all the response in function of the ratio capital omega over the natural frequency. So over here, the magnitude, to go just a little bit faster, will be equal to what? Capital X should be equal to k squared plus c omega squared So what is this term? Remember when you do, maybe let me just do the top. If you do the top, when you have A plus IB, A minus IB, what would this be equal to?
A squared plus B squared.
A squared plus B squared, no? Okay. So that's what we have over here, but I'm taking the square root. And then this was ended up being k minus m omega squared plus c omega squared and the square root. So basically I'm doing two steps in one here. One, we multiply by the conjugate, up and down, and we simplify. Okay? So now using notation omega n squared equal k over m and c over m equal to c omega n. So if you want, since I found those pages, I can refer to them on the class. So let me see. Those pages are okay, 34, 39. Okay. So I'm going to put over here for details, see pages 34 to 39. Okay? So this is going to give us, right away, that x divided by y is equal to 1 plus 4 x squared capital omega natural frequency omega squared square root times the hm omega over omega n times omega n squared. Where the hm capital omega over omega n is equal to what? The long expression we are here. When you see that the expression just repeat themselves, but it's, if I need to rederive everything every single time, we take for it. Let's keep this. And you have the phase angle. Phi equal to tangent minus 1 of minus C omega over omega n cubed 1 plus 4 x squared minus 1 times capital omega n squared. So I know I skip a lot of derivation here, but that could become homework. Okay, so now let's not get lost, because you can easily get lost over here. So what about that page is there we go. Okay, so what is the assumed expression? Our solution is x of t equal to x ei omega t. Let's go to the pages. And we have now all these expressions over here. Look at this one mainly, okay? Oh, there's one here. So I'm finished with this book. Let's get this one. So it should be page 59. Okay. So recalling the assumed solution, which is x of t equal capital X e I omega t. And using expression from page 58, basically is this expression here. So what would be x? X would be y times all this term, no?
Mm-hmm.
Okay? So that's basically what I'm going to copy. We're going to have x of t will be equal to the capital Y 1 plus 4 the damping ratio of the ratio omega over omega n square root times h m omega over omega n omega n squared. Of what do I need to do now with this term over here? Now we're gonna have here E I of what?
Omega t minus 5.
Omega t minus 5. Perfect. So this is the final response for the base excitation. Okay, and the expression for 5, the one you can put it here, but basically it's this one over here, okay? on the previous page. So let me see what is the difference with the one we had first with f of t, where f of t was just general. So we say page 35, no? So 35 to 39. Okay, so basically it's the same form. If you look at it, here it was f sub naught over n. This is expression is the same one and this one. But what happened now is that in here we have just 1/4, no?
Mm-hmm.
Okay, 1/4 in function. And here, what happens because of the relative displacement, you're gonna have the extra term. This will still be the amplitude, okay? But this is the extra term over here. Just this extra term over here. All right, but the way we derived the equation, the solution was identical. I know I skipped some terms because we already spent, I think, almost the whole class last time to derive for the force frequency, no? And here, this is what matters. So last time I gave to you guys a couple of figures. I think I gave you this page over here.
Yes.
All right, so let's kind of look at it if you want. Let me zoom in a little bit. So let's see what those terms wants to say over here. Let's look at the solution. See what is the solution we had before. What is the solution? So this is 4, 57, 58. This is my page 59. Let's just remove it or not. This is from this. Did I give you this one or did I give you another one?
You did give us that one.
This is that one? Okay. So I'm just looking at the ratio over here at the top, the upper TD. That look is the same thing. No, it's 1 plus 4 psi square omega n square root hm omega n. Okay, so it's all the top. All right, so that's the same one. Okay, so from the figure, what can we conclude from the figure? Is that, just like we see over here on the comments, is that where do you have all those curves go at once? So what does that correspond over here? Is that this is like the x over y will be equal to 1. So x equal to y, no?
Mm-hmm.
So basically what I see over here is that when the ratio is lower than 2, the ratio of the frequency is lower than square root of 2, the response output x has a higher amplitude than the base excitation. So basically it means that under this frequency, the x, so how much the car is moving, we have that figure over here. Way too many pages, I'm just going to do the best. So what is x for us? Is how much this is moving, no?
Mm-hmm.
So when this is lower than square root of 2, this is moving at the base excitation. Is that something good or bad? Probably will be bad, no, in many cases.
Mostly, yeah.
In most cases will be bad. But then as soon as you pass that frequency, when the ratio is higher than 2, the response x, so the response of your block on top, is going to be lower than the one of the base excitation. Okay? So let's say you need to do a design. Okay? So what are the things you can choose when you do a design? The value for K and C, no?
Mm-hmm.
So let's say if you want to have a good design that the vibration of this one is going to be much lower than this one, you can probably select values of K and C that will take the response to a ratio of capital omega over omega n that will be higher than square root of 2, no? In that case, whatever the person on n here will feel will be lower than the amplitude of this. Okay? So now, maybe just to do a review over here. What does it mean that here is open? Is that there is no damping, no? If there is no damping, when the frequencies are equal, how is this phenomenon called?
Resonance.
Resonance, meaning that the amplitude of x goes to
Infinity.
infinity. Okay? Now, as you increase the damping, what's going to happen? The amplitude of the vibration should go down. No? So for point 1 is here, but you see as soon as you go to point 2 is here, and it goes down, down, and down. All right? So we have that figure, which is always easy to understand. I mean, not easy, but always gives a lot of information. So these figures, guys, are not difficult to obtain out of a problem using MATLAB. Okay? So sometimes it's a lot easier to do the design from a figure. You know, you can get a lot more information. I think it's a lot easier to get information out of this figure than if you just look at the final equation, which is what? Like, no, I lost it. Like if you look at this equation, no? Okay, you look at this equation, doesn't mean too much, but if you look at it, all this term over here, so this is the amplitude y, this is just a some function, so what is dictating the amplitude is all this term, no? Okay? And if you look at it, that is the term that is plotted over here. Is the one on top. And this is in function of the frequency ratio. Okay, and I give you a similar figure over here for the phase angles. Okay? So I don't think you have the figures.
No, I don't think so, thank you.
Just take this over here. Okay, there's more figures here, we can just skip that. That. And that. So what time is it now?
3:53.
3:53. All right, so let's do one application very quick. Or maybe not that quick, but let's start maybe the application. So, sample problem. Car suspension. Okay, so consider a car traveling over a rough road at a speed v, and we're going to work, so let's say will be given to you in kilometers per hour.
Professor?
Yeah.
I can't really see the left half of the page. Thanks.
All right, yeah. Now I cannot put my hand, so. All right, the suspension system has a spring force K equal to 40 kilonewtons per meter, and a damping C equal to 0.1. The road surface varies sinusoidally with an amplitude capital Y equal to 0.0 meters and a wavelength L equal 6 meters. So the questions here are, write MATLAB code to find X, so the amplitude of the car, so to find X, so to find the X, the car's amplitude for, so two different masses, M equal 600 kilograms, that will correspond to the empty weight of the car, or empty mass of the car, or 1,000 kilograms, which will be loaded Okay, and I'm going to change a little bit here for a certain velocity, and let's say for the velocity, so you calculate it between, let's say, 5 kilometers per hour to whatever, what speed you want to get, like, let's say 120 kilometers per hour. I made up those values, so to make a difference than what I have on there. So this is kilometers per hour. Okay. So here I have the problem statement, but I think it's always easier to do a figure, no? So let's try to do a figure over here. So let's see, how can I plot this? So we have a car. Okay? We model this car by what?
As a block spring damper based system.
Correct, so that's it. We have this, same as before, so this will be our M of the car, K, C. And now maybe I can do this under this form. Let's say it would just be one, that would be like the car, okay? So what do we know about this car? We know that we'll be moving through a rough road. That's some type of sun function, no? All right, so I will say over here. So this is our x, same as before. This will be our y of t. And in this case, what would be the y? Y should be, I guess, the amplitude over here. So what is given to us in this problem? Stop putting values here. Let's say that k is equal to 40 kilonewtons per meter. They don't really give us the c, but they give us they don't really give us the damping value c, but they give us the value for the c value over here, which is 0.1, and the amplitude is what? 0.05 meters. And they tell us that the wavelength is 6. So what is really the wavelength over here? What would that be?
Distance from peak to peak, or
Distance from peak to peak, so we do this one here. This would be how much was it, 6 meters?
yes,
Okay, but also this is what? Remember, this is one cycle, no? And one cycle would be equals to 2 pi, and should be equal to what? The frequency times the period. All right?
Bless you.
Okay. So let me start. What are the equations we need in order to solve the problem? What do we need to solve for? Write the MATLAB code to find x, the car's amplitude. So we need to find the amplitude. We don't need to find anything else. So how can we find the amplitude? What is the expression we have for the amplitude?
Why not times that transfer function?
Correct. So we had the, so what is it, this one? So basically we can use this one here. What is this one? What should you have? You should have x times this y times everything in blue, no? Okay? The transfer function. So we know that x will be equal to y 1 plus 4c squared squared times hm omega over omega n squared. Okay, so that's good, because from this equation we can say where we know the capital Y is equal to what? 0.05, no?
Mhm.
The damping ratio is equal to
0.1.
0.1. Omega n will be equal to the square root of
K over M.
K over n. We know K. We have two different ones, no? Because we have n equal to what? 600 and 1000, no? So in our program, we might have to take care of that. Then now we need the capital omega n. Okay. So this, the way I do this normally is the following form. So what is F is the frequency. Okay? So F, what are the units for F?
Hertz,
Hertz, and 1 hertz is what?
1 per second.
1 over second. Okay. So now we need to be able to relate what if we look at the product? The velocity
And the wavelength.
and the wavelength. So just thinking of the units, how could you relate the frequency to the wavelength?
The velocity divided by wavelength.
So it will be velocity. So can I change maybe this? Yeah. So it will be v divided by L, no? Because basically, what do you have? You have millisecond divided by meters equal 1 over seconds. Okay? So from over here, we know that the frequency will be equals to V over L, and what will be capital omega? What will be the units for capital omega?
Radian per second.
Radians per second. So capital omega will be equal to what if we put in function of F?
2 pi F.
2 pi F, so in this case will be equal to 2 pi V over L.
Professor, could you move the paper a little bit?
Yeah, sorry. Thank you. So, I mean, any questions so far? Okay. So now, let's try to go to MATLAB and program this, no?
All right.
I need a bit of your help over here. So, and since I changed it, oops, no. Home, I'm not working computer. All right. All right, over here, so let's go to MATLAB. So I guess this is what we did last time, I guess. Example for stamping. I'm trying to see if we can use one of them.
I want to use this expression here, no? So,
That'd be nice.
yeah, that would be nice. So let's save this one, so I can do this one, so file, save as. How do we save this one?
Example base excitation.
Example, yeah, example base excitation. Okay, so let's see what we can use from this one, because I hate this stuff here. How can I eliminate this part over here, the bottom part?
I think the arrow on the right side. Maybe not.
You can at least minimize it.
Yeah, there you go.
Okay, I'd rather work with this. Okay, so in this case, we have to modify this, because what they have, m will be equal to what? Two values, no? So 600 and 1000.
Yep.
Then we have k equals to 40 exponential 3, no? We don't have c, but we have this one.
Yes.
Okay, so we have omega. So we might have to do this a little bit different, no?
You're gonna wanna change M, you didn't do the final bracket.
Yeah. So, alright, so we really have to do here a loop, no? So for, because we have two masses, no?
Ah,
So let's say for, I know it's only two, but for I equals 1 to 2. Is that going to do 1, 2? Yeah, no?
I think so.
But for 1 here. For I equal 1 to 2, we want omega of I to be equal to k divided by m of I. Alright? So now that we have the omega, what can we solve for this? Is that going to change our damping ratio? No, no.
Damping's constant.
The damping constant, but we don't have the response, so I think we can eliminate this line here. Now capital omega here, all right, we say capital omega to be equal to what? 2 times pi times velocity
Divided by the wavelength.
divided by the wavelength. But we say that the velocity would be what?
Of vector values from 5 to 120.
So
Converted to meters per
vector,
second.
what can we do here? What do we say, from 0 or from something else?
5.
This is from 5 to 120.
5, so we do every 5, that way would be,
Sure.
how do I do this stuff? 5, 5, 120?
Sure.
Is that the way?
Although, shouldn't we convert it to meters per second instead of kilometers per hour?
Yes, I guess we can do that. Would that work over here? Do we do it now?
Or we could just convert the endpoints to it and let MATLAB do the interpolation.
No, I tried to say is that will it work if I put parentheses here?
Oh,
If I do this?
yeah, should work.
That should work. And now I can just put to, what is the transformation? So it's 1 kilometer is 1,000 meters, no?
Mm-hmm.
And 1 hour is 3,600, no?
Yep.
So that should do it.
You might need to do dot times.
Yeah, so kilometers per hour to meters second. Okay, so now let's see what happens. So I'm gonna need this, I'm gonna need this, I'm gonna need this. Alright, so this is gonna take V, but this is gonna be different values for V. So I want to do just one at a time. So maybe it will be different. I think it was a command called linspace.
That'll work.
Is it bracket or? I don't know. I mean, we'll find out. I think it's 5 to 120, and then you can put how many values you want, no?
Yeah, that sounds right.
So how many values are we? It would be like 5 times 20 would be 100, so 22 for every 5, basically.
Alright.
We can put less, no, but I'm just trying to do this. So now at least we can do then a loop, another loop, no? We're gonna work on it.
You could.
There's probably a more elegant way to do this, but as I'm doing it with you at the same time, so from 1 to 22, here we put V of J. And that should only take one value, no? I hope. So that should do it now. We have the omega, then we can have the R, that should not change. So the little omega, capital omega over omega I. So we have 1 over omega I square. We have all those ratios. So now we don't need this, no? We can plot the response, but I don't think we're gonna need it. We're gonna plot just the amplitude.
Yeah.
So we have x of now should be equal to, maybe let me change this one, is y times the square root of the long term, no?
Mhm.
Which is 1 plus 4 times c square times r square
Yeah.
is r square, yeah,
Yep.
times h times omega I square.
We have to set a value for Z also.
What do you have over here?
Z, we didn't define Z, the constant.
You mean psi?
Yeah.
We never defined the damping ratio.
But we can define that one here, no? So, and, but that's not gonna work.
Yeah, we need to make it build an array.
Yeah. So for these ones I don't care, but for this one, no?
Yeah.
So x. Yeah, we can do this, maybe
I comma j.
I comma I, no?
Um,
Because it's columns, so we want. So I'm thinking about the first column would be for m equals 600.
Okay.
So one for 1000, but I don't know if he here is gonna put,
Yeah, you'd want a j there, I think.
I want a J in there.
I think so. If I understand what you're doing, where each row is.
Yeah, I want that.
Yeah, then you're gonna want a j there.
So hopefully that will work. So then we need plot, what do you want to plot?
Probably v versus x.
I don't want to plot x in function of the velocity, no?
Yeah. Although, shouldn't you reverse those two? Isn't it usually the horizontal axis first?
Yeah.
and
V comma x. So it should be, just a second. So velocity. Amplitude of x, no? In meters.
Oh, and should we split it into two plots based on mass, maybe?
Yeah. Alright, let's try this one just to do one, okay, and
Alright,
comma 1, no?
yep.
And see what happens. Okay, let's do one at a time because I'll be surprised that this works right away. Let's see. But now we don't have the thing is thinking, it's not thinking anymore, no?
Nope, doesn't look like it.
So how can we find out the, how can we get out the other window?
I think go back to view,
View,
Oh, wait.
was it there? Maybe you should click on command.
this one?
No,
I don't know, I think if you go down there and just click command window, it might do it.
do it. Oh, yeah.
Okay, there we go. Undefined function L. That's easy to fix.
Yes.
If that's the only one, obviously. Now I never know what to do.
Oh, one
here.
other thing, I don't think, did we ever define why?
No, we didn't.
No. Y, that's easy, 0.05, no?
Yep.
Yeah.
Now we're gonna need to go here.
Editor?
Editor.
Editor.
Success.
Success, but doesn't look too pretty, no? Alright, it is what it is. We can probably do it better, no? But instead of 22, what could we put over here? Can we change this one to make it better?
Yeah.
I mean, we left 22, no? And then maybe on this one we can put, how can we do this one? I haven't used this one for a long time. Can I change the color over here?
I think so.
So let's say, how do I do like first the type of line, then blue? Does it work that way or no?
You have to do them separate, if I remember.
And then D, why should we make it spread?
I usually don't use the options.
You can probably do it separate, but then you need to do a hold on, no? I don't know. I mean, since they change this stuff all the time anyway, I don't use it that much.
Yeah. All right.
So how can we do the legend here? You want to do which one? I don't know. How do we do this one? Legend? Anyone remember?
I think you can define it from the actual figure itself.
Probably. I'm telling you, I'm absolutely guessing, kind of guessing.
All right.
Not about that.
Looks good.
So basically, I don't know why it's not working the grid on over here, because I didn't put it. But the other days it wasn't working. Oh, it's not working, it's here. Okay, so basically, what is this saying?
It's saying that a higher mass car will get its peak amplitude at a lower velocity.
Okay, but basically remember what we say is that when you drive at this frequency over here, what's gonna happen?
It's going to
What's
vibrate.
happening over here and over here?
It's going to vibrate at its greatest amplitude.
Because that's gonna be the resonance frequency. If it was no damping, at which the natural frequency of the car would be equal to the forcing frequency of the road, no? So that's like when you go driving your car at a certain speed, it vibrates more than other ones. And then what happens as soon as you pass that speed?
Decrease.
It starts decreasing. Okay? So anything you can say about this one? What is the best way to pass, let's say if you have a big bump on the road? Looking at this, doesn't mean you need to do it, but is it high speed or low speed?
Theoretically faster, but
The faster you go, theoretically,
Theoretically.
the less you're gonna feel it, no?
I don't think so.
But this is what it's saying, or not?
Net, yeah.
Okay? So, I guess that's it, no? Do I just save this into the canvas and that's it?
Sounds good.
So meters per second.
Vaporize the speed bump, so it won't go away.
All right, so it's base excitation.
You still don't feel the same thing.
It didn't do that bad, that MATLAB code. I thought it was gonna be worse.
Maybe your test, like,
So canvas here.
right in there, into a bucket concrete. But it's not-
So announcements,
Has to be careful.
assignments. Where did I put all that stuff? In announcements?
It's spectacular. Yeah.
Yeah. So MATLAB files. Edit. So for here, what base excitation. Files, upload this file, choose file. What is it? Okay? So I know you have your exams. What about for tomorrow, you look a little bit more at your exams and see if we can solve some of the problems in class.
Sounds good.
The truth, I haven't done a single one, so it will be completely new to me, okay?
What
But you can
time?
help me. I mean, you should have the printout because you submitted. So bring a copy of your exams and maybe you can help me out to see how we can find the solution a bit faster, okay?
Alright.
I don't think we're gonna be able to do all of them, but let's see if we can at least do a couple of them.
Alright.
What time tomorrow for class?
Very good question.
I have work from 1 until 11 p.m.
At night?
Yes.
I'm supposed to have class with the other one at 10.
I work from 7:30 a.m. until like 5, unfortunately, so.
So you work tomorrow?
Yeah.
So you're gonna do this one. So we could do probably this one for the other people. You wanna do this 11:30?
Sure. Back to the old time.
That's the old time, and we do whatever we can, and whatever, we put online, whatever we find, okay?
Yeah, or like if you can write it down and just put it on.
Yeah, I don't know if it's gonna be too pretty when the writing, because
Right.
all the time, we'll be doing everything together, but I try
Right.
to write it down and still we do the video.
Sure, yeah,
Okay?
yeah. I can send you some notes. All right, shoot me a text. Awesome, man, thank you.
Okay.
So we want a consensus.